Please go ahead.
Okay, got it. Okay, thanks, Nima, for the nice introduction. Yeah, so I've been attending to this seminar for a couple of weeks, a couple of times, and I guess I'm the first one that's going to talk a little bit about compilers. So yeah, so I'm not an architecture guy. We do work on architectures because we have to, and I have fun doing that. But my main concern is like, how can we make those benefits in architectures visible for applications? And so today I'm going to be talking about racetrack memories, which I think are memories that are not very well known. And so I will give a bit of the basic ideas, architectures, and I'm going to talk about code generation. And at the end, I'm going to show you something that we're recently doing for in-memory computing. So that, because this is about in-memories, not only about memories. Okay, so let me give you a brief introduction of what that is that we do here in my group. So as I said, so a big motivation of what we do here for compilers and languages and so on, methodologies, is the evolution of computing. And I think you all know this kind of thing, right? So in '99, this was the cover of a book by Nickel Dot and Panda, talking about the complexity of systems on chip. And in 2012, I was working with a system on chip from Texas Instruments that included an ARM quad core and a bunch of VLW DSPs, a very complex to program. And that's where we were developing like methodologies to program these kind of things. Today, we have even more complexity, right? We have cyber physical systems, hybrid memory systems, emerging technologies, including in-memory computing. And that's here, this is a diagram of a PCM device. And yeah, so all these heterogeneous things, in-memory computing stuff will bring a lot of complexity into hardware. So hardware has become a lot more complex and a lot more heterogeneous. On the other side, I think we have a lot of software is ubiquitous, right? So a lot of people are doing programming complex machines, maybe not necessarily with CS or E backgrounds. And today the issue is that all this heterogeneity has permeated domains that were not common before, right? Heterogeneous systems have been there for a long time for very small niches, right? Like people working on a modem for 3G or something, they were doing very heterogeneous architectures, very complex bus systems and memory subsystems. Today, the difference is that we have all this heterogeneity in systems all over the place. And I think we all know that software is then an enabler for economic, scientific, or being development and stuff like that. Right? Here in the picture of that black hole wouldn't work without very complex number crunching. We work also on application in fluid dynamics, like the one in the middle, and also things like in the embedded domain, like systems like the AUTOSAR adaptive platform is including a lot of complexity from distributed systems, service-oriented, and all this has to run with real-time stuff. I think that, so this slide just goes to show you what the motivation is for the thing of research that we do. So this golden era in computer architecture, including, of course, memory computing, requires changes and maybe new ways of thinking about how to create methodologies to design and program these devices, okay? Yeah, so one particular focus of this talk is, of course, the memory wall. And I think all of you would know that plot from ISCA 2009, where you see this diminishing, or the gap between the increase in the number of cores and the slower pace in which DRAM increases, right? The motivation for all these architectures that you see on the right, right, where we have or high memory bandwidth, high bandwidth memory, and all these kind of things. The fact as well that, for instance, in this paper over here, the fact that 62.5% of the energy in consumer devices goes into the memory. So there's a lot of data here, and but I think if you have attended some of the other talks before me, you will see much better introductions or much better motivations to look into the memory subsystem. Okay, so that's kind of a brief introduction to what we do and a little bit of the focus of this talk. Okay, so this is what I'm going to be talking about today. So I'm going to explain to you what racetrack memories are, and then talk a little bit about optimization. So that's something that we've been doing in the last 3 years. And as I said at the end, something about in RTM computing in general, but also something that we are working on in our group. Good, so let's get started. So Nima mentioned that I am with the Center for Advancing Electronics Dresden, and that means, or that got me to work very closely with people doing technology and physicists and circuit guys and device guys. And so it has been very exciting, but of course I cannot replace those people. So I can go only a little bit deeper as a software guy into understanding the phenomena that we are dealing with. So that's why if I can explain you how this works, but I'll like into details, I'll be outside of my comfort zone. So, but anyway, what is this racetrack memory? So the idea of the racetrack memory is that you have some magnetic nanowires that can transport bits, and the bits are encoded as magnetic spins, right? And these magnetic spins are non-volatile. Okay. And this technology has been there for quite some time. So here you see some of the original papers in 2007, where this phenomena was presented. And in this figure, what you see is that you have this is a kind of the magnetic nanowire. And so you have some different spins. So you have here some spin up, this goes down. And once you pass some currents, so there's going to be some torque transfer between the charges that are moving and the spins. And that effectively what happens is that the spins or the elements move. So if you see this thing here, the separation between the up and the down moves a little bit to the right. That's kind of the effect. That's what happens. And so that's what you can think of this as kind of a shift register where you're moving bits, you're moving bits, shifting bits left and right. So that's kind of the phenomena that we had in 2007, sorry. The problem with this technology is that it was not very reliable. It had a couple of problems, right? So it could be, for instance, these magnetic fields could influence each other, right? So if you have two nanowires like this very, very close together, those magnetic fields were not local, so you could have some kind of crosstalk between the wires. Also, the speed was not very good. It was very difficult to control when to stop this shifting. So there were some papers in 2013, 2014 that improved this by having some heterogeneous structures. So here, what you see here is the magnetic nanowire now in 3D, and it's built on top of a platinum substrate. And for some reasons that I cannot really explain, this helped and reduce some of the effects that I was talking about before. So when we started working on this technology with Stuart Parkin, who is kind of the inventor of this thing, and some of these papers here are from Stuart Parkin, he was working on this kind of more complex heterogeneous structures where you kind of have this platinum substrate, and then you have two magnetic nanowires put on top of each other. And so, to my understanding, what happens here is that when you now try to shift the bits, the magnetic fields are actually contained very locally within the structure, meaning that there is very little crosstalk, and it has also a lot of other interesting properties. Like, for instance, you basically when you move the bits, there is almost no inertia, right? So you can really nicely control when you speed them up and also when you stop them, if you want to read a bit. Okay, so this is what happens throughout the years. So I think in a paper we call this generation 1 or 2. This is generation 3, and today we talked about the generation 4 of these devices, solving many of the issues that were known to racetrack memories in the past. Okay, so this is kind of the device, and now how do we build memories with these things? So now you can arrange those nanowires horizontally in a substrate or vertically, as shown here, right? So if you have them vertically, you could actually put them together like in this array here in a very compact structure. You could store or you could keep all those nanowires together. And now the idea is that every nanowire here would store multiple bits. So as you can see here, the blue ones and the red ones would be like the zeros and the ones. And with the current, you could shift those bits, and then somewhere like here in this region here, you would have an access transistor to read the value of that bit. Okay, so what you see here is that the number of bits in the cell, because the cell is the nanowire, is this is the other way around, is much bigger than the numbers of ports, right? So you have much more bits than you have ports, and that means that you can actually pack this memory quite densely. Right? You don't have one access transistor per bit as in other technologies, or for a couple of bits, but you would have one access transistor per maybe 128 bits or something like that. So that makes these memories potentially very, very dense. So that's why I say here around 100 magnetic domains, and they could be shifted, and the speed at which this magnetic domains can move can reach to the 100 meters per second, which is actually quite fast because these are nanowires, right? Okay, so in the access transistor, what it is an MTJ, right? So it will just sense the resistance state depending on whether you have whether these things align. So to read this, you would have some fixed magnetization domain, and so for instance, these two are up, then you will sense lower resistance states, and if they are in the opposite direction, anti-parallel, then you would measure a high resistance state, and you will know that there is a 1 or 0 depending how you interpret these things. Okay, so that's how you put kind of a nanowire. Then the other thing is that the access transistor actually kind of dominates the area overhead. So what this figure here shows is that by kind of offsetting the nanowires, so this would be the nanowires, the racetracks, you could then offset them and have the access MOS transistors kind of overlapping in the same area, and that way you can make very compact designs where you can have multiple racetrack together with overlapping area of their individual access transistors. Good. So now we kind of understood a little bit of the physics, as much as I can explain that, and then we understood how we can store bits into this, and the other question is, how do you architect a memory subsystem? This is shown here in this figure. So this is a typical organization. So the idea, what you do is you have a normal organization of the memory into banks, into subarrays, and then in each subarray you would have multiple what we call DVCs, and DVC stands for domain block cluster. So by the way, we call them racetrack memories, but you can also find them as domain wall memories, right? Because that thing that separates the spins is called a wall. It's like a wall that separates the bit, the spin up or the spin down or whatever, right? So that's why this is called a domain block cluster. So each domain block cluster, as shown here, that's kind of the particular thing of this memory, is that you would have these tracks. So these are the nanowires. So now the bits are stored here vertically in this representation, and then you could think of having here, for instance, 32 tracks. So you could read in parallel 32 bits, right? So that would be your word, or 64 or whatever, right? So that would be the word that you read, and you could think of all these tracks being shifted in lockstep, right? So if you want to access this word here, you would have to shift the domains to reach the port, and I think here the port will be this red thing, and now you can read that data. And if you need another one, then you have to shift back or forwards, whatever it is, right? And so for that to work, you need some extra hardware in your design. So you need some drivers for the shift current. So you have to pass current through these nanowires to assert the shift. And somewhere you also have to store the positions of the shift of the heads if you leave the ports where they are, right? If you always reset the port position, then you have to store anything. But if you leave the ports where they land, then you have to remember where they were, because next time you get a new memory access request, you need to compute in which direction to shift. Okay. And for that, there are, like what I'm talking about here, there's different port management policies, and you can look at those details, for instance, in this paper over here. Okay, some extra thing that you have into these nanowires is that something that you have to take note of is that you need so-called overflow bits. So here, this would be kind of a layout. So this would be the actual data. And then you need this overflow domain. So you need some empty space, because for instance, if you want to access this one, then you need to shift everything so that the one is under the read access port. So if you do that, it means that these empty domains will be filled with the data that you have here, right? This 100 would be somewhere here. So you need to accommodate for place over there so that that data is not destroyed. So and that's why you need overflow bits on both sides of the racetrack. The other thing that you need, especially for earlier technologies, and since you have some shifting errors, meaning that you may want to shift by one, but perhaps the thing was not really under control, so it shifted by 2, or it shifted by 0, right? So those are called shift errors. And there's been proposals to protect against those errors. And here's just an example of one of those proposals. And it's a very simple one where you have kind of a constant pattern, right? You have 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. And so since you know that you wanted to shift by 1, you know what will be the next pattern, right? So if you have 1, 1, and you know that you're going to shift by 1 in one direction, you know that the next pattern should be 0, 1. And so by checking that pattern against the pattern that you actually see, you can determine that, oh, I didn't shift, I shifted by 2, or I didn't shift, and you can actually correct that shifting error. If you have an error by more than 1 position, that's not going to be fixed, and there are some other schemes to protect against other kind of errors. So as you can see here, this scheme that I'm showing here has a lot of overhead because you need to store this pattern, and you need that pattern as almost as big as your actual data, right? Okay, so but these are details, and there is research around this, how people have dealt with errors. Okay, how do RTMs fare compared to other technologies? So you can find these tables in different papers. Some of those tables are by us. So this is a paper that we published, as I said, with help with the colleagues in Max Planck, led by Stuart Parking. And so if you look at this table, you see, okay, RTM is really cool. And that's why we started working on this with these memories. Why so cool? Because you see that the cell size is very small, right, compared to SRAM. But it has latencies that actually compete with SRAM. So you have, it's very slow, it's very small, but the latency is quite competitive to SRAM. And here you see that the latency changes from 3 to 150, or from 1 to 100, depending how you measure this. And the reason why this can be so high is because of the shifting problem, right? So if you want to access a bit that is 100 positions away from the access port, then you need to wait 100 shifts, or maybe 100 cycles. And that's why this latency is variable, which is kind of the drawback of this technology, right? That you don't know what the latency is going to be if you want to access data, because that depends on what kind of data you accessed before. And so when we talk about optimization, that's mostly what I'm just going to be talking about. How can we reduce these shifting effects by clever optimizations or by compiler optimizations? Okay, something else that you see here is that the write endurance for this technology is quite high. So 10 to the 16, that's very good compared to other non-volatile memories. So the read energy, write energy, it's around what you get in SRAM. It has very low leakage power, and so the retention period is about years, right? So it kind of meets a lot of the requirements, but of course it's still in prototyping stage. Let me check the time. Good. So I collected here some examples so you see that there are some work from other people that have looked into this. I prepared these slides before I knew that actually Venkatesan was going to be in the panel. So and I guess, Nima, you said that he received a Best Paper Award. So I guess this was the Best Paper Award, but that's just me guessing. And so he proposed an architecture to use racetrack memories for caches. And so his idea was we can build like 1-bit racetrack cells, meaning that you don't have to shift, and those you can use for tag arrays, and that you can use also for placing hot data into those arrays, so you don't have to suffer from the shifts if you want to access hot data. And then you could have n-bit tracks for less critical data, right? Data that you don't have access so much. You have some papers also looking into exploring these non-volatile properties of our RTM to build lookup tables for FPGAs. You also have works looking into GPU register files implemented with racetracks. And there are some works in in-memory computing that I'm just going to go give more details in the third section of this talk. Okay, so hopefully you more or less understood the basics of racetracks. Right? I think the basic is that you have a nanowire where you can shift bits, So you have that's why it is a very dense array. And the problem is that you all have these shifts to access data. Of course, you can have multiple ports to reduce the effect of shifting, but the more ports you have, the less dense you can have your array. Okay. Good. So let's look at some optimizations to get around those shifting issues. So before going into some details, so this is kind of the, if I don't say anything else, this is kind of the assumption. So we have for the experiments, we built some simulators. This one over here in particular is called RT-Sim. And this was open source and kind of received traces or results from other simulators like Gen 5. And we're going to be talking about a system with a CPU core, some instruction memory, some off-shift interface. We're going to be talking a lot of optimizations for Scratchpad. And maybe if time allows, I'll also talk about this interface to DRAM. Let's see how far we get. So I'm going to talk about some optimizations, in particular scalar placement, like how do we put variables into this memory, instruction placement, and tensors, which is kind of the more interesting part. And maybe depending on the time, I will skip some slides so that we have some time for the in-memory computing part. But I just want to, for instance, give this so that you understand how Racetracks is more or less kind of a game changer when you think about placing data as a compiler guy, as I am. So that's why I'm going to look at a problem that is a very small problem. It's a very simple problem, so that it is easy for us to understand in this short time. And that is the problem of placing variables in the stack. Right? So say I have a function that accesses these 6 variables, and for whatever reason I know in which order they are accessed. So it accesses B, then C, then A, then E, then F. And so this, if you think of a traditional system, A, B, C, D, E, F, all those variables are going to be mapped to the stack of the function. And that's usually, that goes into SRAM, into cache or something. And it doesn't really matter in which order you map those variables, because memory is a random access. But if you think about Racetrack memories, it does matter, because depending where you map them, you will have to shift more or less. I just noted there is something in the chat, so I want to see. Okay, no, that was a private message. Okay, so just to give you an idea, so this would be like a placement in alphabetical order, or maybe that would be just the placement that the compiler will assume, because it just doesn't matter. So we'll just put the variables up there. This would be another one with some weird order. And so if you go and look at this trace and go from, for instance, here, if you go from B to C, if you imagine you start here from B to C, you don't have to jump anything, you just have to shift by 1. Here from B to C, you have to shift by 2. Then you go from C to A. So from C to A, you have to shift by 4. Here from C to A, you only have to shift by 1. And so the placement 2 is actually quite better, right? So placement 2 here would require for this very short trace would require only 19 shifts as opposed to 51 shifts by the other placement. And that's kind of the like the problem that we started working on. I think that was the first problem that we looked at when we started working with Racetrack Memories. Yeah, so for this example, there's a huge gains, and the question was, is this something that we can consistently get by optimizing the layout in memory? I'll spare you the details. So yeah, we were able to model this problem as an integer linear program problem, very similar to what happens to some algorithms that we found in the literature for mapping things to DSP, to digital signal processors. And so to keep the story short, so we analyzed already the heuristics that were proposed for placing data into DSPs, and we extended these heuristics for our purposes. And so this would be this is the heuristic that we proposed. Okay, so we propose actually these 2 heuristics. So one is called shift reduce, and then optimize that with genetic algorithms in a similar way how it was done in the past, right? So it was also used genetic algorithms in the past to solve this kind of problems. And this is kind of the improvement across 28 different benchmark applications. And you'll see which benchmarks we use in a minute. So yeah, so we could consistently reduce the amount of shifts by being a bit more clever where to put the data. So this plot then shows the energy savings. So the energy savings is we could, if if we take an arbitrary order, in this case, the arbitrary order was the order of first use, we could say 27% energy consumption across all the traces that we use for this analysis. Here you see the individual results for every benchmark that we use. So the nice thing is, since we had this ILP formulation, we could actually know, in some cases, what is the optimum, right? Up until this benchmark, cavity, up until this benchmark, ILP gave us the best solution possible. And so you can see that our heuristic, the blue one, and actually the green one as well, is actually quite close to the optimum. So that made us happy. And then after here, the problem is just too complex to solve exhaustively. And that's why you see that the heuristic can actually sometimes do better than what the ILP reported, because that's just not the optimum. Okay, so this was looking at how to place data in a very simple setup where we're just placing these variables into one domain block cluster, right? So we want to only put variables in those tracks. So then we looked at the problem of how do we extend this so that we can place memory, we can use multiple DVCs. And so the intuition is that, I mean, of course, you can just place them at the port position on every DVCs, but then you're not using the density of the memories, right? Because you have a lot of domains that you're not using. So kind of the trade-off there is how much capacity do you want, how densely you want to pack your data so that you have more memory for other applications compared to how much you want to pay by performance, and reduce that overhead by cleverly layouting the variables in each individual DVC. So this plot is very, very difficult to read. You can see the details in the paper. I think the takeaway here is that we very exhaustively analyze multiple different configurations. And the one that we were proposing is the triangle, that's DMA. And so in most of the cases, the average cost, which we want to minimize, in most of the cases, you see the triangles down here, which is kind of a good indication. So for the details, you can refer to the paper, and also this overview plots here with the results, where you see that latency-wise, our combination of this DMI with our shift reduce was actually quite good in reducing the latency, and similarly here also for energy. Okay, good. So that was a bit quick, and I'm gonna get a bit quick here, maybe in the next slides. So this is about basic log, also so instruction scheduling. This was a collaboration with Jonas Multanen with Pekka in Tampere. And so I think I'm just going to explain the idea of this very briefly. So what you see here is kind of a normal sequential layout of instructions. And so if you imagine that these first instructions are mapped to a DVC, and then the other ones are mapped here. So you would walk through these instructions, and then at some point jump to D0. So you jump somewhere, you'll jump here. If you want to execute this function again, so if you jump back to A, this port will be here. I mean, this data will be at the port. So you will have to shift back so you can access A0. Yeah, so basically, you'll have to undo all the shifts that you did to get to this element to start again. So the idea here by Jonas, quite clever indeed, is that he said, oh, let's those big basic blocks, we will split into two. So what's going to happen is that we're going to be walking first the basic block in the normal order, and then we're going to jump and start walking the basic block in the reverse order. What that means, and if you have two ports, what that means is that the next time you enter the function, the port is going to be already there where you need it. Okay, so you don't have to kind of unwind the tracks to get back to the position that you want to access. If you have two ports, then you are already there if you are lucky, right? Because you kind of first shift in one direction, then shift in the other direction because you're reading in the reverse order. So instead of shifting all the way and all the way back, what you're doing is you read the half in one way, then you read the other half in the other way, and then you're done. So that was quite a clever idea. It was implemented in a simulator for this zero risky processor, and so we worked on the kind of compiler analysis, identifying for which basic blocks this would pay off and whatnot. And then you can refer to either of these two publications for the details. Let me give you at least one plot with results. So this is the energy savings for a given tape length. So which means we only store 8 instructions in a track. And so here what you see is a comparison of energy compared to SRAM across multiple benchmarks. And so in geometrical means, so it means that this system compared with the ISO capacity SRAM would use for them in the memory system only 25% of the energy, which is quite good because I mentioned at the beginning that in consumer 62% of the energy is spent in the memory. So if we reduce that by a fourth, things are a little bit more balanced, right? Okay, so this idea with the basic blocks, right, like kind of accessing in one direction and accessing in another direction, is something that we had already used for tensors, which is the next thing that I want to explain. So we were looking at how can we reduce the latency again and the energy for that matter for tensor contractions in the area of machine learning, and how to do this automatically. And so here you see again more or less the same pattern, right? So if you think of a matrix multiplication, you would go and walk through this row, multiply by this column, right? And then at the point you want to multiply by this column, you have to go back to position A00, right? And then you have to shift back, start at A00 and multiply again by this one. And then again, you have to shift back to position 00 to multiply with the third column. And so this was actually one of the initial works to notice this thing, mapping things in reverse order. This is work with Asif in my group. I think Asif is also here if you have detailed questions. So most of this work is by Asif, and I give the credit at the end. So the idea here was, then now we can lay out these matrices in the following way. You could have this row is mapped in the normal order. This column also in the normal order. But then this column you can actually map in the reverse order, right? So meaning that you go do this multiplication, and then here, instead of rolling back and starting from here, you could start from here because the other column is stored in the reverse order. So you could start multiplicating by this one. So this one times that one, and then you walk this kind of zigzagging, right? So you go back to A00, then forward to A0n-1, and then backwards. And so it's kind of a zigzagging pattern. And of course, this was included into, but not, I mean, also for bigger matrices, also accounting for tiling and all the other optimization that you would do in a compiler. So very briefly on the results here. So here's if you do nothing, so this would be the SRAM. If you do nothing, no optimization. So let's maybe look at the average for different tensor sizes. If you do nothing, it's actually quite bad, right? So you decrease the performance by more than 2, because as I said, you have all this shifting in the middle. And now by the different optimization that we included, you could actually reduce it and be 24% on average faster than SRAM. And that's only the latency part in memory, in energy, sorry. So you'll see quite some improvement again. Here, similar to the instruction case for basic blocks, we save more or less. So we are able, with the optimizations, to bring the energy consumption from, like, say, 60% to more or less 25%. So again, 1/4 of the energy is needed only. So in a follow-up work, we looked into how to move data from DRAM to this scratchpad racetrack memory. So with some contention-aware mapping. I'm not going to go through the details that's in that paper there, but the idea is that you want to remove this sequential access to different rows. By a clever mapping, you can kind of pipeline this and improve performance and also reduce energy. And so these would be the results. So here is a similar thing. So this would be the baseline without any clever mapping of data to DRAM, like interleaving of data in DRAM. And you could save again a little bit of latency and quite some energy. Okay, so the final thing with these optimizations is after we did the manual optimization for these tensors and understanding these patterns, we looked at how can we generalize what we did, like the zigzagging. Like the zigzagging is of course very evident in matrix multiplication, but it's also hidden in tensor contractions in general. But it's also hidden in things like stencils and other things. And so the idea is how can we identify those patterns and change the memory layout or change the operation schedule. And for this, we use polyhedral compilations, which is just a very cool compiler framework with which you can reason about these accesses in a very mathematical, abstract way. And so we extended, or we kind of extended an existing, like the existing polyhedral compiler pipeline, where you get some schedule. So a schedule here means like that you decide when to do what. And so we extended this schedule with some extra optimizations for racetrack memories. So this would be like a scheduler that knows about this zigzagging thing, try to exploit that zigzagging thing, and then also improved the layout of the data in memory. Okay, so that's kind of what we did. Briefly, how that looks like. Maybe let's start with the schedule. So what you have to notice is if you're computing a stencil like this cross stencil that you see here, you will find something similar to what we had in the case of matrix multiplication, right? So you will access, while going through this row, you will access this element, that element, and that element, right? When the stencil moves down here, you will again access those elements. Okay, so there you see that this kind of repetition of, oh, now I have to shift back. And so again, here we use that zigzagging pattern to improve, like to change the schedule, the way we do, in which order do we do the multiplications, so that we can remove a lot of the shifting overhead. And what you see here is, again, like if you have a matrix and you put it into DBCs, this would be like the common layout where you have, in this DBC, you store these variables, in this DBC, you store these variables. But of course, if you access this variable and then this variable, you will have some shifts in between. Whereas if you store the variables kind of in parallel DBCs, you could go to this one, then to this one, then to this one, and only shift when you have to access a receiver. And in that way, you also reduce shifts considerably. So this was kind of the two main contributions of that paper in ACM, in IEEE TCAT in 2020. And this works. So here you see a bunch of benchmarks from polyhedral compilers and also some quite challenging stencils from a weather simulation framework that is called Cosmo. And so to keep the story short, so you see that the amount of shifts are reduced by 90% or something like that. And that improves both energy and performance. The nice thing about this work is that it's a generalization that can be then used for whatever code. Sometimes it just doesn't work because the code doesn't have a pattern that we are interested in, I cannot spot it quickly, but there are, like for instance here, it's not really bringing any of the optimizations that we do. Okay, so let's go to in-RTM computing. So I'll give you some things that have been proposed in the past. This is not from our group. So I told you before that the way an access in racetrack memory works is that you have an MTJ, and this MTJ has a fixed magnetization. You see that here, there's a fixed magnetization here or there. What these people propose is that you could have like two nanowires. So you have a nanowire here, you have another nanowire there. And so in the middle, or here, right? So these are two nanowires like on top of each other. And here in the middle, you could have, again, a readout operation. So here you don't have any fixed magnetization domain. The role of the fixed magnetization is given by the other operands. So here, basically, you can read out through two magnetic nanowires and then compute logical functions, in this case, XOR. Another thing that has been proposed is like a diagram like this one over here, where you have some fixed magnetic domains here. And so and this is kind of the racetrack. And so if you shift from this side, you would be moving a blue spin. If you shift from this side, you would be moving a red spin. And depending on the configuration that you set here, once you read out current through these ports, you can compute different logical functions. And this way you can, again, do some in-memory logic operations. So there are fancier stuff, like in last year in Nature, this paper was published. These are racetracks with like in Y shape, so like they have some forks, and the way these forks work is with chiral effects, like depending on how the domains are configured. So some will go in one way, the other ones in the other way. And there is something that is called this name that I cannot pronounce it. So what happens is that these kind of things will tangle, and if we change the status of one of them, of one of the domains, the other one will also change. And so in that way, you can implement inverters. And then in this paper, they show how to use that that effect to implement NAND NORs and then build a full adder using Racetrack. So, but this is just, as I said, this is a bit more experimental, because I don't know how you would place the access transistors here to actually use that also as a memory and not only as a logic circuit. The final one that I want to show is something that we've been I mean, this is work from Alex Jones in Pittsburgh with Sanjurka Banya in Florida. And so this is called transfer reads. And so what they notice is that if you have, if this is a nanowire here, so usually you read the spins by passing current through the spin, through the domain, right? So you pass some current here, and you can read it that is if that is a 1 or a 0. And so transfer reads means that you pass current through the nanowire and read it here. And so what they notice and report in this paper is that if you pass a current through this nanowire and read it here, the thing that you sense will be related to the amount of ones that you have in those domains, right? So you could think that you can use this to count ones or do group XOR. Right? And we started working with Alex Jones on this, and so we recently worked on an in-memory architecture that uses this phenomenon or these architectures to implement hyperdimensional computing. Right? Some of you may be familiar with hyperdimensional computing. The idea being that you map your data into very high dimensional spaces, like for instance, 10 dimensions. Right? If you say you have something that looks like an integer that fits in 32 bits, but then you just go and model that as something in 10,000 bits. And the motivation for that is like, because that's supposed how our brain, that is supposed how our brain works, that we map data with a lot of dimensions in very complex patterns. And the good thing about that is that you can then, maybe with simple operations, create clusterings and maybe identify classes, right? And that's kind of the motivation behind hyperdimensional computing. So the problem, of course, is that if you have data encoding that is using 10,000 bits, that's very difficult to process in von Neumann architectures, right? Because you have all that von Neumann bottleneck in between. That's why I think HTC is a very nice driver application for in-memory computing architectures. So we did that. Here's a beautiful figure, but it's difficult to explain. Just to tell you what is the pipeline for HTC? What usually happens in HTC, and we're going to look at inference, is that you get some characters. So this is for text recognition to say this is English or this is French, and so you get an encoding for each one of these letters in a high dimensional space. Right? So A is going to give you a vector with 10,000 bits, B another one, and so the way you encode a sequence of characters is by doing some permutation and bundling, and this is explained over here. Right? So you rotate things and then you do an XOR. So you need some operations there to encode the text that you get into a hypervector again. Right? So for each character, you have a hypervector, and at the end, for a sentence or for a piece of text, you will get a hypervector. And then once you have this hypervector, you want to know in which class is this hypervector, right? Is this English? Is this French? And so for that, you need to do a similarity check. And for that, you require, for instance, adding things up and doing a population count. Right? That's kind of there are different ways to implement these operations, but that's an example of how HTC can work. And so basically, you need to account for this shifting, you need to account for XORing, you need to account for summation, and you need to account for population count. And yeah, so without going into further details, so we propose an architecture that it is a memory, so it works like a memory, and it has in every subarray you have a special tile, and in a special tile you have this transfer reads functionality with which you can do XOR, you can do some operations, and in particular, the population count is implemented with some clever Johnson counters that I cannot explain this time. And for us, it was interesting to see how can we do this in the digital domain. So all these kind of things are done in the digital domain, as opposed to some architecture that we found in Nature last year that did it in PCM. So there is an in PCM implementation, or at least of a part of HTC for PCM memories. And I think PCM has been discussed in these webinars a couple of times. Good, let's look at some results, and then I'll stop showing plots. So I'm just gonna report results on inference. Results for training are also okay. So here, at least in the parentheses, the plots for training you can find in the archive publication. So the inference is based on texts with 1,000 words, and so there was an implementation for FPGAs. So we could measure like a 6-time improvement over the FPGA accelerator for inference, and 10 times for training. And here is kind of the runtime breakdown for different benchmarks. And this is the energy, which is a bit more interesting, because what you see here is that so in the FPGA, most of the energy goes into this similarity check. That's the population count. Whereas in our architecture, we're doing that sequentially. So that's why it costs some time, but it's very efficient in terms of energy consumption, right? So we get more or less a 5 times improvement compared to the FPGA, and compared to the in-PCM accelerator that was published in Nature, there was no latency numbers, but at least in the operations encode and similarity check, in the encode we were 10 times as fast as energy efficient, and more or less the same efficiency for the similarity check. In PCM, you can do that using the analog effects of PCM, I think. Okay, so let me summarize this talk. So I think there is some exciting racetrack memory technology out there. I hope it's just going to make it. So I talked a little bit about the principles and recent material advances, right? So this generations of RTMs gave you an idea of how do you put this thing together, how do you make a memory, and I told you about some systems that we have built. Then we talked about hardware, not so much about hardware, but mostly applications and compiler optimizations to get rid of that shifting overhead. That ended up in some generalization with polyhedral compilers, and also for mapping instructions to memories. And the last thing I talked to you was this results for in RTM HTC computing. So in the future, so something that I'm very interested in is we also do work on like domain-specific languages and compiler frameworks. Recently, we've been working quite some. We're doing quite some work in MLIR, which is like a compiler framework to encode the logic of your application, or maybe also to abstract what your hardware can do. And so I'm very interested in kind of also abstracting from this different in-memory computing primitives that are kind of out there, and kind of from these abstractions kind of create a new, if you wish, a new instruction set architecture. So a new set of primitives that we can map down to from programming languages. Okay, that's kind of in this area of research, in this line of work, what my research goals are. So with that, I'd like to thank the people in my team. So here you see their pictures. I mentioned Asif. I hope Asif is still around in case very complex questions pop up. So Asif is the lead author of most of the work that I showed here. We've also collaborated with Tobias Groza and Thorsten Hoffler, and also, as I said, a lot with Stuart Parking and Pekka Jeskelainen. I never know how to pronounce his name, from Tampere. And recently, as I mentioned, with Alex Jones, the work in HTC computing with transfer reads and all that fancy operations in memory come from Alex Jones's group. Okay, thank you very much for your attention. I hope that I get some questions.
Excellent. Thank you very much, Jeronimo. Let me stop the recording.